All right, as we start some more applications of Newton's second law, and we just had a quick review of how to set up these situations, whether you're at rest or whether the system's accelerating, essentially the setup is the same. You want to do the sum of all forces equal to ma. Okay, so let's jot that down. All these problems, the sum of all forces equals ma. So that's pretty much the hardest part, is just to see if you can identify all the forces acting on the object. Now when we start this problem, I'm going to introduce a bit of a curveball here. Do you guys see how that there's two blocks connected by an inner rope? To solve this problem, we actually will treat the two blocks as one block. So instead of talking about 20 kilograms plus 10 kilograms separated by some tension, like if you were to analyze the forces here, I mean, obviously there's a pulling force, correct? The person applies some pulling force. What could you label that? Yeah, you could call that force applied. Now, just through your everyday experience, like what's going to happen to this, these two blocks? They're gonna move, or they're going to accelerate to the right. So there's some tension in this string. There's tension in the string that way, and there's tension in the string this way. Those two forces, what does your hunch tell you about those two? So I heard someone say it. This is a good hunch. The forces in the rope there are the same because it's only one rope. There can only be one force in that rope in this course. Okay, so the tension's the same in that rope no matter which way you look at it. And we actually call this an internal force. We call it an internal force if we think of it actually as like a 30 kilogram block. So that's a better way to think of it. It's a 30 kilogram block with that internal force essentially canceling itself out, and you don't have to worry about it. And then what that does to our original definition is it's that instead of saying the sum of all forces, what we should say is the sum of all external forces. The sum of all external forces acting equals ma. So then if I was to finish off the reading here, there's an applied force to the right, causes the blocks to accelerate. While in motion, the magnitude of the force of friction is given here. Calculate the acceleration. So my force diagram needs one more force pointing the opposite way. Where would you put that? Yeah, where would you put friction? On the right, up top, on the left? On the left? Okay. And we call that force of friction. There's some other forces I'm missing, namely the ones that point vertically. So which forces point vertically? Okay, beautiful. And those ones, of course, are equal and opposite. And in a sense that we don't really have to think about them, in a sense, because they're really not playing too much of a role in the acceleration. The only thing we need is the formula, the formula for force of friction. So again, just on the side here, off to the side, do you guys remember the formula for force of friction? What is it? Mu Fn. So, not sure why there's that big line there. So in a sense, we do need to think about those forces vertically. But like when I go to draw my F net equation, I'm only focused on the horizontal. Why am I only focused on the horizontal? Because that's where the acceleration is, and that's what I'm ultimately trying to solve for. The acceleration is a horizontal situation. However, I do need to understand the vertical forces because the force of friction depends on the vertical force F normal. Now on a flat surface, what do you know? What do you know about Fn and Fg on a flat surface? Yeah, they're equal. So Fn equals Fg on a flat surface. So then we can say, okay, well then F equals mu Fg, which equals mu mg. So there's a formula that we can have ready in our minds when we go to use the force of friction. It's just mu mg for flat surfaces. We'll see later, like when maybe we have a pulley hooked up to an inclined plane, that the force normal is not exactly mu mg. So this is only true for a flat surface. So I take all this information on this really complex diagram with two masses, some internal forces, an applied force, a force of friction, and I simplify it here into this. I call this my total mass. And I know that there's a force applied, and I know that there's a force friction. And we've already talked about the vertical. Did they give us the force applied? And they gave us the force of friction. So you can quickly find the sum of all forces, right? So remember, F net equals ma, and the sum of all forces equals ma. So what's the sum of all the forces? Force applied minus force of friction equals ma. Why did I put one of them positive and one of them negative? They work against each other, right? They work against each other. So one point's that way, one point's this way. If they work against each other, one of them's got to be plus and one of them's got to be minus. Ultimately, it's up to you which one's which, but it's got to be true. Okay? What if this was a brand new situation? What if there was nothing on the left and two of them on the right? Then they'd both be plus. What if there was two on the left and nothing on the right? They can both still be positive. You just have to understand that it's going to be positive in the left direction. So if it opposes each other, one's plus, one's minus. And I typically go with the one that's larger as the plus. So what were the values? F applied is 55, and force of friction is 44.1. So we didn't even have to use that formula. They just gave it to us. And then here we're going to put 30 for the kilograms. And that's it, guys. That's it. So find that difference and then divide by 30. All right, so you got an acceleration of 0. Is it just 2 sig digs? Okay, so we have the acceleration to the right. Now, here comes the bonus question. Yeah, here comes the bonus question. Find the tension in between. Good. So you have to find the tension in between the two masses. This bonus question will show up on your test. It'll probably be with a pulley question though. What we need to do here is find a formula that actually has the tension as a variable. Like if you look in this diagram, I treated those two objects as a whole total, and therefore that internal tension wasn't used. So I don't even have a formula for that here. So how could I get a formula that involves the tension and I'll put a note up here to solve for T, the one that it's pointing to, the one in the middle. Isolate one mass. Sorry, bouncing around. Let's give it 10 seconds so you can make sure you write that down. We're not actually going to do it because we weren't given a coefficient of friction. I'm sure we could find it though. But what we'll do is we'll just show you how, like if I just, remember at the top I said isolate one mass? So essentially what I'm saying is focus on one mass rather than the system, like mass total, rather than mass total. So here, let's just focus on the 10 kilogram mass. What forces are acting on the 10 kilogram mass? Okay, sure, force gravity, which is balanced by force normal. There's still that same force applied by the person, right? You still have this force applied. And then what points to the left? There's a force of friction between the mass and the surface, but there's also one more force. Yeah, there's a tension in the rope. So what we could do is set up another F net equation. You'd have F net equals ma, and then you'd have F applied minus force friction minus tension equals ma. We just solved for A, so then the only unknown would become the tension, and we could solve for the tension. Yeah, you'd say F net equals ma, and then it'd be F applied minus T minus force of friction equals ma. Do you agree with that? Because the applied force points to the right, the tension and the force of friction point to the left. So then to solve for T, I'd have to move the ma to the other side to solve for T. Now I can't do this actually because they didn't give me enough information. I mean, we probably could figure it out, but we'll leave it because we're going to do this again later on. We're going to do this again later on. Are we good on this slide? Going once, going twice? Okay, let's talk about ropes and pulleys. And we'll try to get you guys in the lab tomorrow and Wednesday so you can have experience playing with these things. So even in like first year university, they always just say that the ropes and the pulleys are going to be ignored in terms of their mass and their friction. And I don't know about the second bullet, they have a negligible effect on the system. Because what we'll see is, like, when we get into the lab and we try to relate the theory to the reality, we'll actually see quite a huge discrepancy in what we think is going to happen and to what actually happens. Because there is some friction and mass in the rope and pulley. But nevertheless, the theory remains the same. Draw the free body diagram, write the net force equation, and then use algebra. Okay, so as you can see in this problem, you have tension in the rope as the challenge, just like on the last slide. So we're going to calculate the acceleration of the pulley system below. So, like, at this point in time, if you look at this picture, which one's larger, M1 or M2? And it's obvious by the picture they use a bigger square. So maybe, like, right now there's a person, like, holding it so that it doesn't accelerate. Because, like, what do you think is going to happen if somebody let go of that situation? M1 will go down and M2 will go until M1 hits the ground. Good. Because then the forces would be balanced by the ground, right? So right now, there's a person, like, holding their finger on the mass, and then they let go. So what happens when they let go? You guys just mentioned that. I'll just jot this over here. Motion, like this. That's all I'll just jot down. So all I'll ask you guys to do in the next 30 seconds is to just identify the forces acting on this system. Take you about 30 seconds. Just right on the diagram, draw the forces while this thing is in motion. Okay? Not while it's on the ground here, like while it's in motion. Let's take a look at M1. It has a force due to gravity, but it's also connected to a string that's connected to M2, so there must be something pulling it up. Let's call that tension in the string. Call it T. Now, while this thing is in motion, not while it's just sitting here at rest, while it's in motion, we know that M2 is going to be yanked up. So there has to be some up force. Call it the tension. Is it the same tension as in the other diagram? Is this the same tension as this tension? It's the same string, right? Imagine the two masses are pulling across the pulley. Like, if you flick the string here, if you flick the string here, would it feel roughly the same? I mean, it's the same string, so the tension is throughout the string. That's something you have to understand. The tension is the same throughout the string. Let's just jot that down. Okay, so we know that M2 is going to go up. So how would you relate the FG compared to the first mass? Which FG is larger, that one or that one? FG1 is larger than, because FG1 has larger mass. Okay, so when you draw this arrow, just don't draw it as big. And they can't both be FG, right? Good morning, Mr. Poon. This will be FG1 and this one will be FG2. You look like you mean business. So here's the deal. We can think of the pulley as a mechanism that just changes the direction of the force. So jot this down. The pulley changes the direction of the forces. Well, what do I mean by that? If I was to draw a free body diagram with M1 over here and M2 over here, with this tension as an internal force, what I can do is now, as I can ignore this tension. In a sense, those tensions cancel out, because if I use the pulley just changes the direction. So if I extend the string horizontally, left and right, then these tension forces essentially cancel each other out. So like one points to the right, one points to the left, and essentially that internal force is canceled. So all we have is the larger force due to M1 versus the smaller force due to mass 2. Now if you look at this picture that I've drawn, it's just a horizontal force diagram now, with Fg versus Fg in a fight. Who's going to win that fight? The Fg1 is larger, so it's going to be pulled to the left, which is equivalent in the diagram to being pulled down on the left here. Alright, so then when you write this, F net equals ma, what's the sum of all forces on the left side? Beautiful. Fg1. Oh, I ran out of space there. Fg1 minus Fg2. And then here comes the dicey part. What is the mass of the system? Would it be both of them combined? Good. Good, good, good. So here you're going to put an M total here. And I'm going to put mass of total system. Mass of total system. So when you go to sub in I'll just write it again, whatever. Okay, so Fg1, 5 times G. Is it okay if I just write 5G? And then what's going to be minus what? 3G. And this is going to equal 8A. So what's 5G minus 3G? Yeah, 2G. And then to solve for A, all we have to do is divide out by 8. So the acceleration is going to be 1/4 g. It's 1/4 of 9.81 meters per second square. So 9.81 divided by 4, I got 2.45. Now I just want you to think of the reasonableness of that answer. Like, what if the M1 just fell in free fall without any string attached to it? What acceleration would it fall at? 9.81. Now if you connect that same mass around a rope, around a pulley, and then attach some opposing force, like some other mass on the other side, does it make sense that it doesn't fall as fast? And then it turns out, just because of the way that the masses were, that it ended up being 1/4 of 9.81. It doesn't have, like, it'll be different all the time, right? So I'm going to let you guys try this rather than me droning on at the front, the whole block. So you can find some practice questions on this situation on this page here in your homework book. Okay, so if you got into this page on your homework, we're going to try number 18 first. That's the first one we're going to do. All right, go to your notes now, and we're going to solve essentially the same problem, but this time we're going to be given the acceleration, and you have to actually solve for the unknown mass. So if you take a look at this problem, the acceleration is clockwise. So clockwise, that's going to be rotating. It's in the notes, should be really close, probably a couple pages over. It's past all these. So just 4 slides over. Okay, so that's clockwise. If they're telling you that it's accelerating clockwise, which mass is heavier, M or capital M? Little m has to have more mass because it's rotating clockwise. Capital M is going up, lowercase m is going, so this one must be more massive. So if I was to analyze this situation, I'd call this FG capital M, and then this one would be FG for lowercase m. And I know that there's a tension here and a tension here. So what we can do is we can ignore internal tension, treat this system as a total mass, the larger force is Fg lowercase m, and the smaller force is Fg caps lock M. Does anybody have any issues with what I've done here? Ignoring the internal tension. So it's like, imagine those strings connect the masses such that whatever happens to one of them is going to happen to the other, in the sense that it's just one large mass, one large system with 2 opposing forces. All the pulley does is take those horizontal forces and make them vertical. So we can analyze it in that sense. So just like before, F net equals MA. Which one's larger? Fg lowercase m take away Fg uppercase m, and that equals mass total times acceleration. Alright, so now all we gotta do is plug in what we know and solve for the missing mass, which is capital M. So we need capital M. Okay, so this one's mg, this one's capital Mg. Mass total would be lowercase m plus uppercase m. And I'm just going to pause it there. Okay, so let's plug in what we know. Lowercase m, what are you going to put for lowercase m? Don't say 250 either. Good, 0.25, because it has to be in kilograms. So 0.25 times 9.81 minus capital M times 9.81 equals lowercase m 0.25 plus capital M times 1.6. Okay, starting from the left, 0.25 times 9.81, I got 2.4525 minus 9.81 capital M equals. Now what are you going to do with the right side? You have a bracket, a binomial, times a coefficient. What can you do? Is it pretty obvious? Yes, expand, multiply it in, distribute. Absolutely. So you get 1.6 times 0.25. So that's 0.4 plus 1.6 capital M. So you have an equation where you have m's and constants. So put all the m's on one side. And put the numbers on the other. Okay, so I've run out of space, so I'm going to do it up here. 2.4525 minus 0.4 equals 1.6 m plus 9.81 m. I got 11.41 m. And this is 2.0525. Solving for m, divide out the coefficient. And I get 180 grams. Okay, so now you guys can try number 19. And we'll do 15 and 16 maybe tomorrow.